Hi everyone. So here we will do an example problem on Doppler effect. I have particularly chosen problem number 86 from Tipler and Mosca's chapter 15 because this is a problem where we can show Doppler effect working in sort of different situations. As you can see, this problem has three parts, A, B, and C, and each part we will use a different setup for the problem to solve the problem. But in any case, we will always use the master formula for Doppler effect, which I have written over here. So the master formula is that Fr, which is the received frequency, is equal to Fs, the source frequency, multiplied by V, which is the speed of sound, plus UR. R is the receiver. So V plus UR means the speed of sound plus the speed of the receiver, divided by V minus US, where US is the source speed. And just remember that this formula is applicable with the appropriate signs when the source and observer, which is the receiver, is moving toward each other, right? So for instance, if the source and the observer were moving away from each other, or if the source was moving to the observer but the observer was moving away from the source, we have to appropriately change the signs in this equation, right? All right, and the additional information that we know is that V equals 343 meter per second. This is the speed of sound in air, right? So we're going to use that information. All right, so let's first read the problem. It says a car is approaching a reflecting wall. A stationary observer behind the car hears a sound of frequency 745 hertz from the car horn and a sound of frequency 863 hertz from the wall. How fast is the car traveling? What is the frequency of the car horn? And what frequency does the driver hear reflected from the wall? Okay, so clearly there are several scenarios, right? So I have drawn a figure. The figure shows you the stationary observer, which is a receiver in this case. And then there's a car, which is the source of the sound, which is moving. The car is moving toward a wall, which is also in some sense a receiver, right? I mean, the wall is receiving the sound and then reflecting it back. Okay, so we're going to analyze this problem now. So the first thing we're going to do is we're going to focus on this. The stationary observer behind the car hears the sound of frequency 745 hertz. So we're going to call that frequency F1. So F1 is equal to 745 hertz. Okay, so can we express this in terms of all the variables that we know? So F1 is the received frequency received by the stationary observer, right? So then we go to the master formula and look at this and write F1 equals Fs, which is Fs is the frequency that the car is emitting, multiplied by V plus UR. Now, UR represents the speed of the receiver, but here the receiver or the observer is stationary, so there is no UR, divided by V minus US. So US is the source. In our case, the source is the car. The car is actually moving away from the observer. If it was moving toward the observer, this would have been a negative sign. But now the car is moving away, so this is going to be a positive sign. So we get V plus VC. Okay, so this is F1. F1 equals FSV over V plus VC. The issue is that we do not know VS. We know V. We do not know VC. So we really have two unknowns. Fs is not known and VC is not known. So we sort of need another equation to go further. So in that case, we are actually going to look at the second provided piece of information, which is the frequency that gets reflected from the wall and comes back to the stationary observer, right? So that we will call F2. So F2 is going to be our 863 hertz. Great, so we have another piece of information. Let's see if we can express that in terms of our variables. So in order to do that, we'll write F2. So remember, F2 is the frequency that got reflected by the wall. Now, the wall and the observer, the stationary observer, they are not moving relative to each other. I mean, it's a wall, right? So it's stationary. And the observer, by definition, is also stationary in this problem. So since these two are not moving relative to each other, there's no Doppler effect, which means that whatever sound the wall receives, when it gets reflected, the stationary observer receives the exact same frequency. So all we have to do is figure out what is the frequency of sound that the wall receives. Okay, so that's going to be F2 equals Fs, okay, times, again, the wall, which is the receiver, is not moving. So this is V. There is no receiver speed. The source is moving, but this time the source is actually moving toward the receiver. So this is going to be V minus Vc. Okay, so we have F1 and F2. We know F1 and F2. There are two unknowns, Fs and Vc. And in fact, the first two parts of the problem, A, how fast is the car traveling, which is Vc, and what is the frequency of the car horn, Fs, those are the two unknowns. So our first step will be to take this first formula and write, just take the numerator of the right-hand side and write Fs times V is equal to F1 times V plus Vc. And from the second formula, we have Fs times V is equal to F2 times V minus Vc. Great, so now we have two formulae, but look, the left-hand sides are the same. So we can set the right-hand sides equal to each other. So we get F1 times V plus Vc is equal to F2 times V minus Vc, right? And so from here, we can now simplify this equation, and we want to find Vc. So we'll bring all the terms that have Vc in them to the same side. So we're going to do F1 plus F2 times Vc. So that will be equal to, and we're going to take all the other terms to the other side. So we have F2 minus F1 times V. Okay, so then this tells us that Vc must be equal to F2 minus F1 divided by F2 plus F1 times V. Okay, so this is our answer for the speed of the car. So the speed of the car is equal to the difference between the two frequencies divided by the sum of the two frequencies multiplied by V. Okay, so at this stage, I don't want to work out the numbers. We can do that later. As you can see, the right-hand side of this equation, everything is known. We know F2, we know F1, we know V. So we can actually work out what Vc is. We'll do that at a later stage. So this is the answer to part A. Okay, now let's move on and try to solve part B. So for part B, we now want to find Fs, right? What is the frequency of the car horn? So Fs is what we want to find. Okay, so since we want to find Fs, we could just take this formula and plug it back into one of our equations, but I'm going to do it in a slightly different way. I'm going to sort of take these two equations, and from here, last time we eliminated Fs times V, this time we're going to try to eliminate Vc. So what we could do is from this first equation over here, we can rewrite that, and that would look like Fs over F1 times V is equal to V plus Vc. And then the second equation can be written as Fs over F2 multiplied by V is equal to V minus Vc. And note that now if I just add the two equations together, then just by adding the two equations together, I get Fs over F1 plus Fs over F2, right? Both multiplied together by V is equal to 2 times V. And how did I do that? Well, if I look at just the right hand sides, VC and positive VC and negative VC, they cancel with each other. V plus V is 2V. And on the other side, I just factored out the V, and that's how I got this result. So again, the other added benefit is that V will cancel from these two sides. So I can just factor out the Fs, and if I do that, I get within the parentheses, I get F1 plus F2 divided by F1, F2, and that is equal to 2. And then it's easy to simplify this, and we find Fs is equal to 2 times F1, F2 divided by F1 plus F2. And that is, again, my result for the source frequency, or the frequency that the car horn, when the car horn is blowing, that's the frequency. Again, here we'll leave it as a formula like this, and we're going to work out the numerical result in a later part. Let's carry on, and we move on to part C. So in part C, the question is, what frequency does the car driver hear reflected from the wall. Okay, so this is the reflected from the wall. So now this is a little more tricky, right? Because we have two parts here. So first the car is moving toward the wall, and then the the reflected wave is moving toward the car. Okay, so let's think about the first part. We have already worked that out. So the first part is this thing F2, right? So F2 was equal to Fs times V over V minus Vc. This is the frequency that the wall is receiving from the car. But now the same received frequency is going toward the car. So the car is now another receiver, right? So this is part C, right? So if I can just quickly go back to my original setup, right? So here for part C, car is also a receiver, right? So since the car is also a receiver, we have to again invoke our master formula. So this time, let's call this new frequency F3. So F3 is the received frequency. And what is the source frequency? It is what the wall is reflecting. So that's going to be F2. So F3 equals F2 multiplied by this time the receiver is the car and the wall in part C. So if I can again go back here. So for the reflected wave of part C, the wall is the source, right? So since so this is only for the reflected wave. So is this only for the reflected wave? Is this true? So for the reflected wave, the wall is now the source. So that source is not moving, which means in the denominator we have a V, right? There's no U source, but the receiver is moving toward the source. So since the receiver is moving toward the source, right? So we still have that as V plus VC. Why VC? Because the source is now VC, so and it's moving toward the source. Okay. All right, so now we can combine these two equations, right? I can plug back the F2 into this equation and I get this equal to Fc times V divided by V minus Vc multiplied by V plus Vc divided by V. V's will cancel, so I get F3 is equal to Fs, yeah? Fs times V plus Vc over V minus Vc. Okay, yeah, but what was Fs, right? So Fs, we know that Fs from the previous formula is a 2f1 f2 over f1 plus f2. We can actually plug that in. So we will get 2 times f1 f2 divided by f1 plus f2. You don't really have to do that, but I usually like writing all my answers in terms of the original provided variables that we know. Of course, here we don't know Vc either. So we have to do one more step where we go back to our original equation that we found, this F1 times V plus Vc equals F2 times V minus Vc. And from here, we can just write V plus Vc divided by V minus Vc. So this ratio, if I look at this equation over here, that ratio is just equal to F2 divided by F1. And so we can take this and then plug it back into this last part of our answer. So we get 2 times F1 F2 divided by F1 plus F2. And the second part, this V plus Vc over V minus Vc is just F2 divided by F1. So 2 times F2 divided by F1. This F1 cancels with the first F1. So our final answer for F3 is equal to 2 times F2 squared divided by F1 plus F2. Again, this is our final answer. In a second, we will now focus on using numbers to work out each part of this solution. Now that we have worked out the individual formulae for our final results, we can just take the numbers and plug them in. And for doing that, my favorite software is this Mathematica. You can actually use Wolfram Development Platform, or if you want, you can use your calculator to do this final part. So all we're going to do is we're going to plug in our numbers and get our final results into these formulae, right? So VC here is equal to F2 minus F1 over F2 plus F1 times V. So I've written out exactly that formula, and my V is 343 meter per second. F1 is 745, F2 is 863. Note that this final result will be in meter per second because the first part is just a ratio frequency, so it doesn't have any units. The second part is the speed, which has units of meter per second, so our left-hand side must also have units of meter per second. So let's see what we get if we run this. We get, okay, so this is not giving us an exact result. We want more in terms of a number. So what we are going to do is we are going to do that. So we find that this is 25.17. So that tells us that the car, if I can just go back and enlarge this, the car is moving with a speed of 25.17 meter per second, right? And that is our numerical answer for this part of the problem. The second part of the problem is the frequency of the car horn. So this one, again, we can work that out. So I'm gonna make sure that this time we get an answer in terms of decimal digits. So that's the result. We get that this is 799.67. 799.67. I'm just going to write it as 800 hertz. So it's roughly 800 hertz. That's how much, it's very close to 800 hertz. That's how much the frequency of the car horn is. And of course, you can see that this frequency of the car horn is actually in between the two frequencies that are given to us, 745 hertz and 863 hertz, right? Okay, so that's the frequency of the car horn. And what's the frequency that the driver of the car receives when the wave is reflected by the wall? So this is the third part of the problem. And again, here we're gonna want an answer in terms of decimals. So we get 926.33. So this answer is 926.33 hertz. All right, so that's our three-part Doppler effect problem. Generally, this will cover all sorts of different kinds of Doppler effect problem. If you have any questions, please email me at bhattach@ltu.edu. Thanks a lot.